Okay, in this video we're going to talk a little bit about something called Markovnikov's rule. It's to do with how alkenes add small molecules across the double bond. If we look at something like this alkene, for example, what we have seen previously is that when we add water in the presence of an acid catalyst, and we can represent acid by just H+, and if you remember, that water plus acid catalyst gives us H3O+, and what that involves is addition of OH and hydrogen across the double bond, we get something that looks like this. So in other words, the acid-catalyzed addition of water across the double bond gives us an alcohol. Now the one thing about this reaction right here is what we have on both sides of the double bond is exactly the same, so therefore it doesn't matter where the alcohol goes. And we can also talk about a similar reaction, because we're going to be seeing this later on. A similar reaction where we add in something like HCl or HBr. HCl, as you guys know, is a strong acid, so essentially it splits up into H+ and Cl-. And through a mechanism that's very similar to this one, in fact a little bit less complex, we have a similar situation where both of these two species add across the double bond, and because the starting alkene is essentially symmetrical, it doesn't matter which group goes where. In other words, where the chlorine goes or where the hydrogen goes. They both go on carbon double bonds, or the carbons that were originally present in the double bond, but it just doesn't matter which. The issue comes up that Markovnikov's rule helps to discuss is a situation like this. Let's say we have an alkene kind of like this guy. And let's just take a look at a mechanism. Okay, and let's just use HCl. Let's push some arrows here. As you have seen before, alkenes undergo these things called addition reactions because the alkene has that relatively weak pi bond that can break and send out to attack something that's electrophilic. The electron density around the pi bond, around the double bond, makes it nucleophilic, and if there's anything even vaguely electrophilic around, or sufficiently electrophilic I should say, such as the hydrogen in HCl because of chlorine's electronegativity relative to hydrogen, you can have nucleophilic attack at the hydrogen. And as we've seen before, because hydrogen can only have one bond, this hydrogen-chlorine bond has to break, and so what we end up with is a 5-carbon species, just as we had 5 carbons before. And let me just number these here. 1, 2, 3, 4, and 5. Well, as you can see, unlike in this compound, where carbons 2 and 3 are exactly the same, in this compound, carbons 4 and 5 are actually different. I hope everybody can see that. Carbon 4 has a 3-carbon unit coming off it, and 1 hydrogen, and carbon 5 just has 2 hydrogens coming off it. So the question then becomes, the hydrogen that adds across this double bond and adds on one of these 2 carbons, Markovnikov's rule allows us to figure out where that hydrogen goes. Now, rather than just giving you the answer based on Markovnikov's rule, what we're going to do is to look at both of the possible places where the hydrogen could go and see what we're left with. So let's assume the hydrogen goes on carbon number 4. So I'm just going to draw that on here. Okay. And just so you guys can be sure, I'm going to put these hydrogens in. And so what that means is, when I draw those hydrogens in here as well, okay, there was already hydrogen here on carbon number 4, so now effectively there are 2. The issue that we have now on carbon 5 is that we haven't added any new bonds to carbon 5, so therefore that carbon is missing a bond. It's got a plus charge on it. Now what if the other possibility had happened? And what if that hydrogen had actually gone on carbon number 5? So in other words, what if that carbon had 3 hydrogens now on it, and the carbon 4 had its 1 original hydrogen on it, and the carbocation, the positively charged carbon, would then be on carbon number 4. The question is, which of these two is the one that formed? If these two were to get into the UFC octagon and beat the crap out of each other, which one would win? Well, the point is, it's the one that's more stable, the one that's happier. And basically, a carbocation that has more alkyl groups funneling electron density into it is more happy. This is a primary carbocation. This one is secondary. Now, the reason why this one's primary is that the carbon bearing the plus charge only has one other carbon connected to it. Therefore, only one set of carbons pushing electron density into that plus charge and stabilizing it. This guy has 1 carbon here and 1 carbon here. Notice it doesn't matter how long each carbon group is. What matters is the number of carbons attached to the carbon bearing the plus charge. There are 2 groups here pushing electron density into that carbon, making it slightly more stable. And if you heard that, then I think my computer may have just exploded. Of course it hasn't, but it did like to make a funny noise, so whatever. Okay, sorry about that. I don't know what happened. Well, I do know what happened, but never mind. Okay. So what we've just shown here is this is actually describing this thing called Markovnikov rule. And you can actually write this out in words in several different ways. One way is to talk about the location of the hydrogen that gets added in. One way to describe what Markovnikov's rule says is that when you have an unsymmetrical double bond, the hydrogen adds to the carbon that already bears the larger number of hydrogens. Therefore, according to that statement, with 2 hydrogens here and 1 hydrogen here, this hydrogen should add to carbon number 5, and that's what we see. That's a more stable product. Now, the other way to describe Markovnikov's rule is that when a hydrogen adds to a double bond, it adds in such a way as to form the most stable carbocation. In this case, secondary is more stable than primary. Okay? So 2 different ways of describing this thing called Markovnikov's rule. As you can imagine, there is only one other type of carbocation that's more stable than secondary, and we can't come up with it from this structure, but just to give you an idea, if I had a situation like this, where I had a plus charge here, I'm hoping everybody can see, this would be a carbocation with 3 carbon groups around it, and thus 3 potential places to donate electron density, therefore more stable than secondary or tertiary. So the idea of carbocation stability is tertiary, more stable than secondary, more stable than primary. Now, there are some others as well, and we'll talk about those later on, but primarily, at least to begin with, this is our basic idea about carbocation stability. So if we had to then predict some products of Markovnikov of addition to alkenes, based on whether we can apply Markovnikov's rule, let's see if we can do that. Remember that we have to have unsymmetrical alkenes for us to even begin trying to apply Markovnikov's rule. Okay, if I had something like this, cyclohexene, and I ask you guys, okay, what's the structure of the product here? Well, the first thing you'll be able to tell me is there's certainly a 6-membered ring. For one thing, this is an addition reaction. My double bond's going to be gone in the product. Across that double bond, I'm adding hydrogen and chlorine. So I could say, well, there's one product, and the other one could be where I switch the H and Cl, but in that case, the alkene's symmetrical to begin with. The product would be the same either way. So we can't apply Markovnikov's rule. This is the only product that we would get. assuming we aren't thinking about stereochemistry. Now, what if, though, we had something like this? This is the same sort of molecule, except if I was to put a methyl group here. Now I'd say, well, what if I have HCl here instead? Okay. Now we get to a point where the alkene is not symmetrical. So therefore Markovnikov's rule becomes important. The way to draw out the products here, it's actually very simple. What you should do is draw out the carbon skeleton of the molecule without the double bond present, because you know that will have been broken to form the product. So all we know right now is that our product is going to contain 7 carbons, the 7 that we've shown here. And so really what we want to think about is which carbon would the hydrogen go on, for the hydrogen from the HCl. And remember, we are looking for 2 ways, or one of 2 ways, to satisfy Markovnikov's rule. That is, we're looking for these 2 carbons and seeing, first off, which one initially bears the larger number of hydrogens. Well, we have 1 hydrogen here, and we have no hydrogens here. So therefore, Markovnikov's rule would tell us that the hydrogen that we add on should go onto this carbon. In other words, giving us this. And if that's the case, what should go here? Well, it should be a plus charge, and if this is where the plus charge goes, you have your chlorine here. What do you think the chlorine's going to do? Well, the chlorine, as stable as it is, it still has a negative charge. This is very, very electrophilic, and so the chlorine's going to go, hello, plus charge. Do you like me? I'm negative, and I can tell you do because you're positive. That's a really bad joke. In fact, don't ever repeat that, please. And so, here's my methyl, here's my chlorine. I'll leave it up to you as to whether you want to show the hydrogens in the product. But the point is, that is the so-called Markovnikov product from the addition of HCl to 1-methylcyclohexene here. We added the chlorine onto this carbon rather than this one. The hydrogen added to the carbon already bearing the larger number of hydrogens, and we formed the more stable carbocation. If you can just think about it, the carbocation that we have here has 3 carbons around it. Therefore, it's a tertiary carbocation. Let's just draw out the carbocation that we would have formed potentially if the hydrogen had added to the other carbon. If the hydrogen had gone here, our positive charge would have been here. And if you think about that, this is our carbocation, therefore we have 1 carbon next to it, another carbon next to it. This carbocation is tertiary, this carbocation is secondary. This is the one that will fall, this one won't. Okay? And what that means is any possibility of this product with the chlorine going down here is essentially not going to happen. Okay? Because we cannot get here in the first place. So we're always looking, when we have an unsymmetrical alkene, to form the more stable carbocation. Hopefully that makes sense to everybody. Alright, so let's try another couple of things here. Let's actually try, what if I was to do something like this? I'm going to draw out this, and I'm going to put this here, and then this here. Alright, and this time we're going to do something slightly different. In fact, we'll go through the mechanism of this. Okay, H2O, H2SO4. This should be something that you remember from what we've seen previously. What we're going to do first is draw out the product, and let's see if we can figure out the mechanism. The important thing to remember here, when we're adding H2O and H2SO4, is what I said a couple of slides ago. When we have H2O and H+, we have H2O and a H+ catalyst, we're going to be forming an alcohol. We're still going to be following Markovnikov's rule. So let's draw out the product here first. Do you remember what we said before? We draw out the carbon skeleton, so we've got the correct number of carbons, and then we just ask ourselves, the hydrogen is going to go on which carbon of this double bond? Well, 2 hydrogens on this carbon, 1 here, so therefore the hydrogen should go on this N carbon, In other words, if this is carbon 1 and this is carbon 2, the hydrogen should go on here, and the OH should therefore go on here. Let's see if we can do a mechanism for that. Okay, this is exactly the same as the mechanism you've seen for the general addition of water via an acid catalyst to alkenes. It's exactly the same as you've seen before. The only difference is the structure of the initial alkene. So, let's start off just by saying that, well, whenever we have water in the presence of H2SO4, we know that we essentially have water and H+, so of course we're going to form everybody's favorite electrophilic species, which is the hydronium ion, H3O+. Exactly the same as you guys have seen before. And what is the alkene going to do when it comes into contact with this? Which one is going to be the nucleophile and which is the electrophile? Well, this guy's got the positive charge. This has the oxygen with too many bonds. The hydrogen is having its electrons pulled away from it by the oxygen. So this is the electrophile. This is the nucleophile with its electrons from its pi bonds, so that grabs that hydrogen. And as you remember, we've said before, hydrogen can only form one bond. This kicks electrons onto the oxygen. This makes the oxygen happy because now it goes back down to those two bonds again. Remember, the plus charge on oxygen means it's not happy, it's got one bond too many. So what we're going to do now is to draw out our product in terms of where the carbocation is going to go. Remember what we said about Markovnikov rule, the hydrogen adds to the carbon that already bears the larger number of hydrogens, and we talked about it up here. 2 hydrogens here, 1 hydrogen here, therefore the hydrogen goes on here. Okay? Therefore, the carbocation is here. If the hydrogen had gone here, we would have had a primary carbocation. Here we have secondary, therefore it's somewhat more stable, and therefore it's what forms. Also bear in mind though, what else we just formed in our first step. We had our hydronium, and from that we formed some water that is still going to be sticking around. In fact, there's plenty of water around. Anytime you do anything in H2O and H2SO4, there's plenty of water lying around. So that water is going to act as a nucleophile and attack that carbocation, by far the most electrophilic part of the whole molecule. And what we get is the oxygen adding to the carbon. But bear in mind, you haven't shown any arrows to show many bonds breaking in the water, so that means the 2 hydrogens are still connected. There's still a lone pair on the oxygen here, but because the oxygen's got 1 bond too many, what else does it have right now? Well, that's just as we've seen before, it has a plus charge. And we're getting to the last step right now. You remember we said this was an acid-catalyzed process, so essentially this is present, at least initially, in catalytic amounts. So if it was there at the start and it's a catalyst, it has to be there at the end. So how can we go from here to here and reform H3O+? Well, we need to remove hydrogen from here, and the one thing to remove it is another molecule of water that is lying around. Like we said before, there's plenty of it around. So that goes there, grabs that hydrogen, kicks the electrons onto the oxygen, and gives us our product, and reforms the H3O+. Okay. That's the whole mechanism for acid-catalyzed hydrolysis of a non-symmetrical alkene following Markovnikov's rule. Exactly the same as for this guy, except the mechanism here is much less complicated. But either way, we're talking about acid being involved in addition to an alkene. Here the nucleophile was Cl-. Here the nucleophile is water, but either way, the nucleophilic species adds in the same place. And there we go.